So this is the question I've designed for the assignment task for section 6 of the portfolio. In relation to my topic, the hyperbolic paraboloid, I designed my question around a model of an old auto car sales showroom, which can be seen there in the picture on the right hand side. I just thought it was a good idea to design it around this model because it kind of puts the question into a real life context and situation for the students. So reading the question, given is the plan of a hyperbolic paraboloid roof structure ABDC. So students will be given, my peers will be given the outline of the plan to start with. I just thought it would save a bit of time rather than having to draw it out as well. So the corner A is at ground level, so it's on the horizontal plane. Corner B is 10 meters above ground level. Corner C is 12 meters above ground level, and corner D is 1 meter above ground level. So note also it says scale 1:200. So students will have to divide, let's just say for example, 10 meters by 200 and then convert that to millimeters. I just thought this was a bit of an add-on rather than giving them the measurements as they were, say. They have to do a few calculations. So part A reads, complete the given plan and draw the elevation using 6 elements in both directions. Part B, find the traces of the plane director for the edges AB and CD. Part C, find the curvature of the roof along the line AD. And part D, give 2 reasons why a hyperbolic paraboloid is a good structure to use in the construction of a roof and suggest 2 materials which it could be built with. So I just included that last part there because I think STEM is becoming so much more important. So moving into our solution, firstly for part A, students will have to complete the elevation and the given plan. So what we do is we project our corners up from our plan to our elevation, and students will mark off the heights that they have found. So after changing the meters to millimeters and using the scale, A will still be on the XY line anyways. Corner B will be 50 millimeters above the XY line. C will be 60 millimeters above the XY line, and D will be 5 millimeters above the XY line. Then going back to our plan, as it asks us for 6 elements, going in both directions. So students will use the basic construction method of dividing a line into an equal number of parts. So they'll divide each side of the plan into 6 parts. So once they've that done, then they'll join, say for example, division 1 here to division 1 on the opposite side, 2 to 2 on the opposite side, and so on. And then 1 to 1 on this side, 2 to 2, and so on. And then they'll find the elements in our elevation. So point 1 is on the line AB, bring 1 up to the elevation, where 1 cuts AB in elevation will give us 1 in elevation. 1 is on CD over here, so bring 1 up to cut CD, and where that cuts CD will give us point 1. So 1 joins to 1, and we'll do the same then for the rest of the elements, and we'll get our curved structure in there. See that curve in there. So that's part A of the question solved. Pretty much easy enough. Just to kind of walk them into the question. Part B then is find the traces of the plane director for the edges AB and CD. Now this question was kind of thrown them in at the deep end. So what they have to do is use the same construction method for showing skew lines as parallel. So basically the line AB and CD are just 2 skew lines anyways. So what they're doing is they're making a copy of the line AB from point D. So that line there is parallel to that line, and they take a level line then from C to cut that line they've brought out from D. So that'll give us point X in our elevation. So now is to find point X in plan. So project X down to plan, and the same thing again then, taking a copy of the line AB from point D. So that line here is parallel to that line. So project that out, and where it cuts the line we brought down from elevation will give us point X in plan. So now we project our corner C through X, and that will give us our angle then we're looking in at to find the edge view of the plane director. So we can project our corners in up then at parallel to this line there. We know it's our true lit line. So if we look along a true lit line then, we'll find the edge view of the plane director, as I just said. So project up our corners parallel to this angle. So they're all going up like that. So we're basically projecting an auxiliary elevation. So what we're doing is we're taking our heights then from our elevation. So A1 will be on the X1, Y1. B1 is 50 millimeters above the X1, Y1. D1 is 5 millimeters above the X1, Y1, and C1 is 60 millimeters above the X1, Y1. So that will find that here then. And we know the plane director is containing the element CD. So that will give us an edge view then of our plane director. So what we can do then is extend the edge view of that down to hit the X1, Y1, as you can see there by the pink line. Then we take that line parallel to the line we projected at. So parallel to this line we project it back to cut our XY line, and that will give us point T, and we can just extend that then, and that will give us our horizontal trace. That's our horizontal trace found there then. We want to find our vertical trace, so we're just basically using the oblique point projection method. So we're taking from our point D, we're taking a line parallel to our horizontal trace to cut the XY line. Then from D in elevation, we take a line straight across, and we take a line up from where we cut our XY line, and that'll give us a point, where that cuts the line we've brought across, will give us a point on our vertical trace. So that's how we find our vertical trace there, and our horizontal trace shown in red. So we know we've proved it's our plane director because we can see that our elements are appearing as parallel. See the way they're not parallel here, but up here they are appearing parallel. So that proves in that we found the plane director. So that's part B of the question solved. Part C is find the curvature of the roof along the line AD. So what students are going to have to do is they're going to have to project an auxiliary elevation to find the curvature and the true shape of the line. So what to do is they join A to D in plan, and where this line cuts the more horizontal elements, mark them as points. I think then this one here as well, you just needed an extra point for the curve. So you mark where AD cuts this line here. So as I said, you're projecting an auxiliary elevation. So our X2, Y2, can go parallel to the line AD in plan. So we can project out our points then perpendicular to this X2, Y2 line and the line AD. So perpendicular to them two lines. And we need to find our heights for our points. So firstly, we need to find our heights then in elevation. So we know, say for example, point A1 is on the line 1, 1. So bring point A1 up to cut 1, 1 in elevation, and that'll give us A1 in elevation. So we can do the same then for the rest of the points. And what we do is we take that distance on our compass and we can step it off here then, and that'll give us the point. So we do that for the rest of our points. And point A is on the XY line, so A will be on the X2, Y2 line. So once we've all our points found in, we can freehand in our curve there. That will show us the curvature of the line AD. So that's part C covered. And part D then is a STEM question, as I said. So I just have it solved over here. So I'll be looking for students to say that the fact a hyperbolic paraboloid is a doubly ruled surface means it's easy to construct by using a series of straight structural members. They gain strength through their shape. The curvature of the structure reduces its tendency to buckle in compression. Also, by being braced in two directions, they experience no bending and are able to withstand an unequal loading. So that will be showing how a hyperbolic paraboloid is a good structure to use for a roof. So that would be the first part of that question, part D solved. And then part 2 would ask us to name 2 materials it could be built from. So it could be built using wood or steel for the elements and then cladded over. So that's a solution anyways to the assessment question I designed for my peers. And I feel it's challenging enough, but it is very definitely doable, and time shouldn't be too bad. Maybe finding the plane director could take a bit of time, but the rest of it isn't too bad. And yeah, that's basically it.